So yeah, is there any doubt on filter? No. Okay. Okay. So then we'll go to the we'll start from the CRLH line. So today's class will be mostly short part only because we'll cover some theory and we'll show you some ideas. But the theory is not so elaborate here. Uh, yeah, hopefully it will be short today. So yeah, before starting, I will ask how many people have heard about or have read about CRLH lines or left-handed metamaterials, left-handed transmission line, artificial transmission line. Who has read about it? Anybody here?
No, sir, not heard.
Okay, okay. Okay. So, normally, metamaterial is a very growing and uh, very popular field in microwaves. Not only microwaves, even in photonics, acoustics, in all different fields is being used. So, what metamaterial does is, it has a it can create artificial properties what you don't get generally in uh, real materials what you available in the nature, like you know the materials what you get in normally has a epsilon r and mu r, that is relative permittivity and permeability is greater than zero. Okay, so not all the cases, like mostly. Some cases where epsilon r is negative. Do you know any example where permittivity is negative? Any material which has gives negative permittivity? It is there. Yeah, actually, it exists. Okay, so I suppose you have not heard about it. So generally the plasma, okay, uh, normal plasma or what actually available in real ionosphere plasma behaves like a negative permittivity material. Okay, epsilon r is negative. So that is one case. And then you can get separately permittivity negative. Sorry, permeability negative. So permeability negative means is like these are negative. What you call magnetic materials. Generally, magnetic materials only has a different mu r, relative mu epsilon permeability. Otherwise, all the normal non-magnetic materials we have a relative mu equals 1. Only epsilon changes, epsilon r, but mu r equals 1. So magnetic materials like ferrites and all, they have a negative permeability. Okay, but as it happens, generally you get them separately. Either mu are negative or epsilon are negative. You never get both of them together in reality. Okay, so what it seen that if you see the definition of refractive index, okay, refractive index is defined by square root of epsilon r mu r. Okay, so if both of them are positive, it's positive. But generally, in the metamaterial theory or concept, it has been shown that if you take both of them minus, negative, mu r is minus as well as epsilon r is also minus. So then square root of mu r and epsilon r, what happens? In between it is inside becomes positive, but it has been shown that actually n becomes the negative refractive index itself becomes negative in this case. When you have both epsilon r and mu r are negative, then it becomes negative cone. And there are a lot of repercussions because of this negative um, uh, refractive index, and that's why there is mostly, there is a complete different domain of metamaterials, right? so which has been used in different aspects of designs of RF, like imaging and even communication, all the different things. It has been, they have a lot of applications and all. So there are many ways people have come up with to design a negative epsilon and mu material, okay, or negative refractive index material. So I don't know if you heard about the first guy who actually first scientist um, who has thrown out light on this concept was, like, long time back, a Russian scientist called Veselago. So he has proposed this theory around the 1950s, but that was only in concept. Conceptually, he has shown what can be, how can be, the negative materials and all. But recently, only around this decade, in um, around the beginning of this century, around 2000, Dr. D.R. Smith and their group, they have actually shown actual demonstration of negative refractive index using SRR. So, or it's also called split ring resonator. Okay. So, split ring resonators are like, is also a 2D material. So, they have designed this kind of things and shown that it is actually possible. So, since then, the rise of metamaterials is going on a very fast track. Okay. And then around the same time, 2000 and all, the another different group come up with a another different type of visualization or explanation for negative material, demonstration for negative refractive index material, or also it is also called left-handed material. Okay. So which is negative refractive index in one term. People have very different names for it. Somebody call it artificial metamaterial, also called DNG material. You might have double negative. Double negative means mu and epsilon both are negative. And also another term is left-handed metamaterial. Left-handed means generally right-handed materials. What happens that the direction of wave propagation and direction of energy propagation is same. Okay. E cross H is generally what we take as the both pointing vector gives you the pointing vector. If you remember, it gives you the direction of power propagation. Okay. And similarly, the direction beta gives you generally the direction of phase propagation. So, or the what you call the um, there are two type of velocities. Okay, one is group velocity and another is just a minute. Okay, so yeah, one other is phase velocity, another is group velocity. Okay, so the thing is sometimes what happens, people have shown for this negative left-handed materials, the direction of phase propagation or in direction of energy propagation or power propagation is actually opposite. That's why it is left-handed. So normal materials are like right-handed. So that's why in the same direction energy propagates as well as phase propagates. Okay. So only in left-handed materials this happens opposite. So so coming back to this, so around 2000, the group led by this Dr. Callows and all, uh, they have demonstrated a transmission line based explanation for a left-handed metamaterial. Okay. So, see, before that, people are talking about this SRR and all. They are not based on transmission line theory. They are generally based on, 3D electromagnetic behavior. Like they actually used to look into mu and epsilon, all these things, refractive index, and Sinen's law, all those were used. But the Scallo's group, they have actually explained all these things in terms of transmission line theory itself. Okay. And as you know, this course itself, or before that, we are very much popular with, familiarized with the um, transmission line theory, so we can relate these things easily. So that's why it is actually called left-handed transmission line, or together is called CRLH, composite right and left-handed metamaterials. Okay. So now we will look into this today's class on how a left-handed metamaterial or using a transmission line, left-handed transmission line can be visualized. Okay. So as you see, these are the very simple transmission lines equations, what also called as telegraphers equations. So if you see this, the basic fundamental equation is one you get in terms of voltage and current for transmission line, and in case of electromagnetic wave propagation, we see the same things in terms of electric field and magnetic field. Only that is the difference. But actually, if you see the terminologies is kind of similar. The gamma is there. Gamma is the propagation constant, which is alpha plus j beta, attenuation and phase shift constant. So the second equations are called Helmholtz equation in electromagnetic wave, right? So if you solve this, generally we know this is the very popular plane wave equation solves. It the solution is in terms of e to the power minus alpha and beta in all these terms comes. It is a sinusoidal wave or harmonic wave, and it is attenuated as well as phase shifted because of the gamma. Okay. And similarly, if you solve the telegrapher's equation for transmission line, you will get a similar equation for voltage and current, because so it will like attenuate when you go through the propagate through the transmission line, and if it is lossy, if it's not lossy, only phase shift happens. And the characteristics of the lines are impedance square root of L over C, and the phase velocity is square root of L into C. Okay. So that is how it is given. So what are these L and C? L and C are traditional transmission lines where it is, the inductance and capacitance over unit length of the transmission line. So you should always remember this unit length factor. Okay. It's not like a actual capacitance. It's per meter or per centimeter, whatever you assume. So now, if you just look into simple transmission line, this is how it is looks, right. So you have a resistance and inductance in the series arm, and a capacitance as well as a lossy element admittance here in the sun term. So this can be represented together as ZS. S means subscript means is a series term, and YP, it is the parallel admittance. Okay, so this whole thing is represented at this. So just note down, or notice this nomenclature carefully, because this is very vital, like how you do, because it will be carried forward in the next slides. ZS is the series means because it is in the series arm. Okay, it represents resistance and the inductance together. So ZS series impedance, and YV is parallel admittance. YP actually means the G, that means the admittance here, this admittance as well as the capacitance together. It represents by YP. So now if you take these things here, the normal, the well-known value of the characteristic impedance comes by R plus J WL by G plus. So this actually you can just replace by ZS by YP. It's as simple as that, because we actually replace these terms with this term here. Okay. Similarly, the gamma is also given as this equation, and we can replace gamma with ZS and YP. Right. Now, in case of a lossless transmission line, generally that is what we assume. What happens? These R and G terms vanish, because there will be very minute loss because of resistive or admittive elements. Okay. So that is it becomes zero. So then only L and C remains. Then what happens? ZS is inductive, YP is capacitive, and this Z naught, it becomes now L over C, and gamma is it becomes this equation j omega root LC. So that is actually nothing but the phase term, right? This phase shift, that is beta omega square root LC. So this is the normal transmission line, or what we call right-handed transmission line, where phase propagation and power propagation happens in same direction. That's why it's right-handed transmission line. Okay. So yeah, till now, do you have any doubt? Any doubt till now? Okay. So yeah,
Sir, can you give one example for right-handed transmission line?
example means see all the transmission lines you are using. If you have also used a transmission line for your microstrip line section, those are all right-handed only. Okay. Right-handed transmission line is whatever you are using. Left-handed is not available. That is why you need a different theory for it. Is it clear?
But we are
What the
not using,
question?
sir.
Sorry,
It
come
exists
again.
theoretically, but not practically. Is it, sir?
Which one, right-handed or left-handed? You are saying
Left-handed, left-handed. Sir.
left-handed was I told you no left-handed transmission line or left-handed metamaterials all are not available at all. So people like this is actually a complete new field. People develop new theory as well as new techniques to demonstrate it. So that is what we are coming to. Yeah. But till now, whatever you are using is right-handed transmission line.
Okay, sir.
Okay. So now, yeah, now note these things. Here, the characteristic impedance as well as beta both are positive. Okay. So that what it rhymes with the the right-handed materials, right-handed transmission line. Okay. That's why both beta and characteristic impedance are positive only. Now let's come to a fictitious situation. Let's imagine a situation when we change these conditions here. Till now, here what was happening? ZS here, the series was term was inductor and the shunt term was a capacitor. Okay. Now let's change this thing. Let's take the capacitor in the series and inductor in the parallel. Okay. So then what happens? Let's say ZS is capacitive, YP is inductive. Then if you put it here in the equations of Z naught and gamma, what happens? Z naught remains same. Is same as 1 square root L over C. That is real. So that means if real, that means you can match and all these things. That's why power can propagate through it. But now you see what is surprising is now gamma because it becomes minus here. There is a J term here and it is minus also. That is what it is very surprising. So that means beta becomes negative. So your phase shift is actually now negative compared to the previous case where it was omega root LC. Okay, here it is opposite, and not only opposite, here omega also comes in the in denominator now. Okay, so this is what actually is a negative material, negative or left-handed material. Okay, see, just by interchanging the capacitor inductor, it becomes gamma is negative. So what are the repercussions of it? Now we'll go to that. What happens? So generally, how we characterize these transmission lines and all is one way to do it is called dispersion diagram. What is dispersion diagram? It is a plot between phase shift, that means beta, and omega, that means the angular frequency. So a plot between beta and omega is called a dispersion diagram. So that is how we generally use it. You see, normal right-handed materials is omega square root LC. So it is linear. Okay, beta versus omega you plot you see is linear. But for this fictitious or artificial line, we thought that by just by interchanging capacitor inductor, beta becomes negative. So here see what happens. The phase shift is actually becoming negative. Here it was positive, so it is actually negative. So that means if you go across the transmission line, what should actually happen? You should have a phase shift in positive terms, but is it actually giving you a negative phase shift? Okay, so that is the is the surprising thing from this theory you get. Generally, what happens if you go across the across a transmission line, the wave will propagate and there will be phase delay. But because of this negative phase shift, what will happen? You will get a phase advance. So it actually acts like completely opposite. So again, that is why it is negative left-handed. And the plot also you see it is no more linear. So near beta equals 0, omega becomes still goes to infinitely because of 1 over omega equation, and then it reduces very drastically. It's like a hyperbolic plot. Now, yeah, this is what we are actually proposing for this fictitious cells, right? So the capacitance is in the series arm and inductance is in the shunt term. That is the change we have done compared to the normal traditional transmission line. This is what in the bottom one, okay? So where L is in series and C, and because of this, you saw the change in materials. The change in properties from the dispersion diagram. So is this part till now, is it clear or do you have any doubt here? Okay. So now we'll see what happens from here. So now what is the way to implement this? Okay. Now, so before coming to this, see what are the uses of it? The uses are if you have a negative if you can generate a negative phase shift, okay, so that can give you a lot of advantages. So one way is that you can just reduce your length of the normal line, transmission line or normal circuits whatever you design. If you use these lines, these left-handed lines, or what we'll call this later as CRLH line, composite line, you can reduce your length, okay, that is one way. And then you can use for defined sections like generally you can actually make all your devices and materials as very compact. I mean that means again coming back to um, reducing the length or the not only length, it is the overall size reduction. And there are other uses like you can use this for making couplers as well as power dividers as well as antenna fabrication everywhere, every antenna design, all these designs, this has been used, lot of uses has been found. Okay, so this one of the uses we'll see now here. Okay.
Is this commercially available? The whatever the proposed this one
No, it is your design, you have to design it. It is just like
or the
designing
right hand
others.
material, whatever it will.
Yes, we are coming to that. Yeah, we are coming to that. Yeah. So now thing is normal transmission line, we don't have capacitor in the series and inductor in the shunt. We have opposite, right? So how do we do this? How do we fabricate this? So one simple way is to just put some lumped elements. If we just use a lumped element capacitor in series and inductor in the shunt, so it should give you the behavior like this, okay? Because normal transmission line or microstrip line, we cannot do it. It is not possible. So we can just use a lumped component here, okay? That is one simple way to do it. Okay, you can refer to this paper here. This is from Callows. And see, this is as old as 2005. So, but the problem is you cannot just put the capacitor inductors there, right? You have to have a uh, pad, soldering pad, and all this. So the moment when you use the soldering pads and all, that acts like a right-handed material also. So then you will have both of these right-handed and left-handed transmission line together. Okay. So the because that means you have normal transmission line or normal microstrip line as well as these lambda elements together. When that happens, that means composite right and left handed transmission line. That is the why this name comes. Okay. That is the the main theory between the main reason behind calling it CRLH. So when you do a transmission line demonstration and use capacitor inductor together, you have both right-handed and left-handed things coming together. Now coming back to it, see how this actually can be designed. So what people have actually done, if you see this picture, so this Kalos group and all, they have actually demonstrated using inductor and capacitor together. And there is another way to have a capacitor inductor is, inductor we have seen a shunted stub can replace a inductor. But capacitor in a series arm is actually very difficult. You cannot add it like this. So one way is to do a IDC or interdigital capacitor. Okay, this is the one of the other different ways. But a simplest way is just using lumped components. So now this, what is this composite behavior here? That is what is shown here. Capacitance is series, inductor in also series, and again in the sun term also you have two series and sorry, the capacitor inductor both in the sun term also together. So that is why it comes from composite, right-handed and left-handed together it comes. And what will be the dispersion diagram now? See, left one is the dispersion diagram only for left-handed line, and for the right-handed line this is the dispersion diagram. Okay, so together it become like this. Now if you add both of them composite materials for some frequency, if you see notice properly, the y-axis is the frequency arm. So before this frequency or above this frequency it acts like a right-handed material, and below this frequency here it behaves like a left-handed material. Okay, so that is why this composite behavior also comes. Okay, so yeah, by the way, this paper here, this explains these things very you know you know very elaborately. They have explained this theory, this paper from magazine article from IEEE Microwave magazine, and it shows several um, examples and all how it can be used. So this paper I will share with you. Who all are like very interested, you can actually go through this. Okay. Okay. So now let's go to the analysis of this theory. Okay. When it is a composite, when you have capacitor and inductor in the series, let's replace it by ZS. And similarly, capacitor inductor in the sun term is YP. When you put this in this equation again, coming back to the equation of characteristic impedance and beta. Okay, because you remember all the transmission lines has these two main characteristics. One is characteristic impedance Z naught, another is gamma or is the component beta. That is the phase shift constant. So if you take that, yeah, and if you plot, it should give you actually this plot. So beta is here. If you see, uh, it is dependent on frequency. That's why here also what we see in this dispersion plot. So this plot is actually this beta equation. If you plot, you will get a dispersion plot like this. Okay. Now in some special cases is that when this LSCS equals LPCP, what is LSCS? In the series arm, S means for series inductor capacitor and P means for the sun term. Then if you replace this, Z not become like this, LS by CP, and beta becomes like this. In this equation, if you replace this, it becomes like this. Okay. And then what happens? If beta is 0, in which you can calculate it. Now, if beta has to be 0, what should be the frequency? That means this is this point here. This is the origin here. In this point, if you go above here, in this point, beta is actually 0. That means if you operate at this frequency of transmission line, there will not be any phase shift at all. See how curious this is. Like If you operate at this frequency in this transmission line, in this artificially designed transmission line, there will not be any phase shift. Okay. So this special case is called balanced CRLH line. Okay. This is called balanced CRLH line, where beta becomes 0. And sometimes it will happen that for some design lines, this might not converge. The left and right may not converge. So then it will be called unbalanced line. Here, you see here. In the left-handed line, left-handed plot, left-hand plot is what actually we are seeing. Right-handed and left-hand line converge at omega b, where phase becomes 0. But here if you see, the right-handed and left-handed line actually does not converge. There is a gap between. So this is called actually stop band. So that means this also you can actually use for a band pass filter design or band stop filter design. Because below omega 1, it will pass. Above omega 2, it will pass. But in between omega 2, there is no phase shift available. There is no beta. So that means here it will act like a stop band. And the other sections are right and left is the pass band. Okay. And there are some several design constants. One of the constant is if you design a unit cell like this, the length must be less than lambda by 4. Okay. At omega b, that means in the balanced frequency. The length obviously has to be below your design frequency lambda by 4. That you should remember. You cannot take just any length of line. It should be length is lambda by 4. So yeah, that what you are talking about. What are the uses of this? So there are several uses like quarter wavelength section and quarter wavelength transformer and others. Okay, and there are also another very interesting use is in using resonant circuit or tank circuit. So we'll see now how it can behave like a tank circuit also or resonant circuit. So before going there, yeah, do you have any question?
Is there available this particular substrate on the material to
It
which to
is,
implement?
yeah, you can design for any substrate. Yes.
You mean in
Sir,
the Roger substrate?
You can design on any substrate. Yes. Yes.
sir, if possible, can you give some example of this material design, if possible?
Yeah, I will show you one. Yes. This is just using capacitor inductor. You can do it. Yes. If I have shown you one picture also. Yeah. This is from this paper. They have done like this. Okay.
So, sir, if time permits, please do focus on some practical design by using this material so that we will come to know about it.
Yeah, that I will cover only small part because this itself is like a full course. Okay.
Yes, yes,
Metamaterial
yes,
itself.
sir, yes, sir.
Yeah. I will cover only
Yes,
small portion and I will share with you this paper also, which is a very comprehensive paper. You can,
yes, sir.
if you
So,
are
small
interested.
example will lead to us a good design. So, that's why we are
Okay.
asking.
Okay. 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 Okay, so yeah, I am coming to that. Let's before that, this is one of the papers written by this Pramod M from our group and Professor KJ Binay. So they have done a design like this. Okay, so where they have designed a zeroth order resonance. So what happens? Normal right-handed transmission line. So you should follow the beta L equals n pi because the length should be lambda by 2 for a resonant circuit, okay, resonant transmission line. So that means the lowest length you can take is n equals 1. So it should be L will be n pi over beta, okay. That means lambda by 2. Now, for the CRLH line, the thing is, for some frequency, you can actually get beta equals 0, right? If beta is actually 0, that means there is no constraint on the length itself. You can take any length. So that will like drastically reduce the size of your um, unit cell or size of your transmission line circuit. Okay. If beta equals 0, this equation means you don't have any constraint on the length itself. So that is one way is called zeroth order resonance. So this is one unit cell. You can take just a one simple transmission line unit cell itself, CRLH unit cell, where you have a, shunt inductance as well as a series capacitance, and together with the other right-handed materials, it can behave like this. So this is one example. And similarly, the same Pramod has done the same design with a varactor diode also, which can make it a tunable resonator also. Okay, so these are the separate examples, and there are examples on tunable band pass filter as you are saying. So as you see, there are like the implementations. These are with IDC or interdigital lines, and as well as you can use a capacitor inductor also. And these are the uses of the thing like coupler and normal 3 dB power divider. All this everything can be implemented just like simple right-handed transmission line you are using, e- except instead of that you can use this to design the other components, the normal microstrip circuits. But if you remember, this is will not be that simple. The designing will be complex. So obviously to gain something you have to do some effort, right? So, yeah,
I have a
now
question here. What will be the maximum power we will be able to do it? Is there any limitation?
that see, power actually will depend on the substrate. It does not matter on the material. Okay, I mean the design. How much substrate your how much power your substrate can handle, it will depend on that, right? Like how do you
Okay.
know that how much power your design can handle? From the breakdown voltage.
Mm.
Right. So that does not depend on what metal design or what pattern you are drawing on the metal. Obviously, it does not depend on that. It depends on the substrate. And like, the permittivity or permeability properties, what is defined. So all the substrate comes with a plot. If you look into the data sets, they give the behaviors with frequency, how it behaves. So you can obviously, work up to that. They might also, you can find the power values in the data sheet itself.
Yeah,
Okay.
usually it will be in
Hmm.
milliwatt. Whether it will be in watts, around 300, 400 watts is it possible to do?
Yes. See, whatever you have in normal microstrip line, the same you can do it here also. Okay. Yeah. Okay. So coming back
Sir,
to this paper,
sir,
okay, this paper give you a very comprehensive review, and you can actually
yes, sir.
look into this if you are very interested. And they not only do show a 1D design, even a 2D design also shown here. Okay, so I will not go into all of these details. You can, if you are interested, you can look into this. This is see a branch line coupler design, and this is a power divider design. Okay, as well as this is a antenna design. So I see these are like very small size design and so compact. You see, compared to this, the coin here. See, it is so compact. So these are like you can look into this, and they have also designed leaky wave antennas with this same lines and all. So they have lot of applications, and it is very interesting also. And I will share this paper with you. You can actually, I think you can. Mm, you all have access to the chat, right? Here you can see if I put something in the chat. I will share in the chat itself so that you can take it from here.
Sir,
Just a minute.
okay.
Can you download this component here? I just posted in the chat in this paper. You guys see it, right?
Yes, it's downloadable.
Okay, okay, okay. So you can all download and look into it. Okay. Yes, somebody was asking doubt. Yes.
That power handling depends on the copper thickness. For example, 35 microns has got some limit, power limit.
Okay.
Correct me, sir, if I'm wrong.
Is it? No, I have not come across any such constant. But yeah, you might be right. I am not so sure. Yeah, I have not come across any such. But if you have read about it somewhere, or if you have known it from somewhere, it might be. Yeah, I don't know. Yes.
For example, in PCBs, for a higher current rating, we will give higher thickness for the ground.
Okay. 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 Might be true. I am not so sure. If you have come across any document or something, you can share with us. We'll look into it. Huh? Okay, so yeah, now coming back to, I'll show you. So another interesting material is this book. Okay, this book is written by Dr. Kalos and Ito. So, so Dr. Ito and Kalos, they have done this all the works, most of the pioneering works on CRLH line, and this book is written by them. Electromagnetic metamaterials, transmission line theory, and applications. So they give all the design and all everything approach, all everything. So it's not a big book also, only 365 pages. You can also look into it, okay, if interested. Otherwise, this paper is okay. So yeah, coming back to something like some design I have done in ADS. So yeah, see, this was one of the problems. Let's say you have to design a CRLH line. Uh, let's say with a microstrip line is given, the characteristic impedance you have been given, dielectric constant has been given, and you have to find out the capacitor inductor values and the microstrip line parameters, so that you will have a design of CRLH line. Okay, so first is like how to get the balanced condition, right? So balanced condition, I show you there is equation. So that is one thing. And 5 nanohenry, this transmission, the inductance has been given. Okay, then this is the sun term. This is serpent mount inductor, because additionally you have to add it. And the condition is that the balanced operation F naught is at 3 gigahertz. That is what you have to do. That means the phase shift should be 0 at 3 gigahertz. Okay. And the equivalent circuit and all, this was one problem we have solved. Okay. So from this, you have to come here. So what do we do? We have to follow the equations there. So that is why this MATLAB equation was written. Um, you can follow, see the C, capacitance, frequency, all these are given. And the LP is the parallel arm inductance, or the SMD capacitor inductance, 5 nanohenry is given. CP is what we have to calculate, the series arm capacitance. Yeah, series capacitance as well as shunt. All these things you have to calculate. So now how do we take all this? So these just follow the equations. If you see CSLS equals LPCP was the condition for balanced. That if you do, you will find the CS here, value of CS here, this one. This is what 2.2 into 1.183 picofarad we have found out here through this equation. Then once this is known, the another constant is what you have to find out is D. What is D? D is the length of unit cell. Okay. What the length, here, this transmission line sections you are using, right? But what is the length? That is found out through this equation. And this comes from, if you remember, yeah, this all comes from here, this equation. Okay. So if you know all this, and you have to remember this, all this capacitor inductor, which is already there in the, for a right-handed material, it is has to be normalized with del Z. Okay. But what you are putting additionally, that is not normalized. That is what one thing you should actually remember. You see, that is why this value, it is L del Z, C del Z. Because what you get, this capacitor and inductance, these are actually per unit length. Okay, L and C is per unit length. That's why del Z is multiplied to give the same unit. But the parallel arm LP and CS, what you are adding, the lumped components or SMD components, they are not normalized. Okay, So that is what, if you have put here in these values, LP, this del Z values, from here you can calculate the D, or the length of the unit cell. And that has to be less than lambda by 4. That you should remember. That is the condition given for the CRLH line design. Okay. So once we use all this equation, we same equation, from that we calculate the D. And when that is done, then we get the beta for right-handed and beta for left-handed. Again, the same equation, omega square root LSC base, and here left-handed is 1 omega 1 over omega this. And this plot has been plotted here from MATLAB. Okay. So I have plotted this here. The phase shift, that means beta into D, and here frequency. Okay. If you plot here, you see up to some frequency here, you have negative phase shift, and after sometimes you get right-handed or positive. And see, in the 3 gigahertz, what was the condition? At 3 gigahertz, you should have balanced condition, balanced operation. So that is what we have here. You see, close to 3 gigahertz, the phase shift is 0. That means it is a balanced operation. This section is before, above 3 gigahertz is right-handed, and below 3 gigahertz is left-handed. So it's negative material here. Okay. And then it has been, it has been designed in ADS. And the capacitor inductor is what we will put. These are the lumped components. And there will be some transmission line section which for padding or soldering, as well as it will also behave like for the right-handed material. Then if you simulate in ADS, you get these plots. Okay. So here, if you notice here, the S21, S11 plot is like as normal as it is. But the interesting part is here, the left plot. What is beta versus frequency plot here? Phase of S21 is actually gives you beta. So here if you see at 3 gigahertz, if you notice here, see here at 3 gigahertz, phase is 0. That is means it is a balanced operation. And that is what we actually designed. Okay. So this is one design. Okay. And you can look into this code here also and follow this yourself and do this. Although there will not be any assignment on this part, you can follow yourself this code and design yourself for your understanding. But it takes some time, okay, to understand. Go through the theory carefully and then use this code to design it. And the same thing you can, go to, in the transmission line section or the layout, it will look like this. Okay. Transmission line section, and in between you can put the capacitor inductors, and it gives the same results in the co-simulation. This is the co-simulation result. And you see, you get the same thing with some minute variation. Obviously, the 3D simulation will change some of the thing. So it is not exactly zero now, but it's close to that same performance. Okay, so that is what, yeah, this is what today's part all about. So yeah, up to this only. And I will suggest, if you are really interested, go through the paper, and I will tell you to, just do the same assignment yourself using this code and just copy and see yourself. Okay. Yeah.
The capacitor and the inductor is a physical part connected over the
Yes, SMD. Yes, SMD component.
SMD. So in case that you are saying 3 gigahertz, so any inductor or capacitor, they'll have some self-resonant frequency. So how do you select that capacitor and inductor part?
So you have to actually
The
take the
characteristics
model.
of
Yeah, you have to take the model from the data sheet and put it here. Okay, and then you have to tune little bit and see.
no, the device itself will have some resonant frequency, no? Self-resonant frequency. That how will you
Self-resonant.
take care? Any
Uh,
any
uh-huh.
capacitor or inductor, they themselves will have some self-resonant frequency.
Because of the parasitics you are saying.
Okay. So
Uh-huh.
in this design,
Mm-hmm.
how you overcome that?
No, we don't overcome that. See, these are ideal components, right? So that's why, see, in any microstrip line, forget about this design, any microstrip line design, if you have to take the component what you want, what do? We take the value from datasheet itself with parasitics and everything. Okay, that we put here and then replace it, and then we simulate it, right? That is what you have to do. Okay, so today I will finish it here and then meet next week. Okay. You go through the paper I shared with you, and then we will meet next week. Okay. And if you have any doubts and all, we will see.